Have you ever seen a swarm of a million drones painting these incredible pictures in the sky and wondered, how? How do they do it with no one actually flying them? Well, today we're diving into a paper that might just have the secret. And it turns out the answer isn't just in the code, it's in the very shape of space itself. So let's get right into it. This is one of the absolute biggest puzzles in AI and robotics. How do you get global order, a massive group of independent things acting like a single intelligent being, just from simple local rules? It's a huge challenge. And this is what we call the swarm challenge. It's like trying to conduct an orchestra with a million musicians. You can't possibly give each one individual instructions. No way. They have to listen to their neighbors and somehow find the rhythm all by themselves. That's the problem we're up against with drone swarms or software bots. And our usual ways of tackling this? Yep, they're hitting a brick wall. So what are these walls? What are the limits? To really get why the ideas in this paper are such a breakthrough, we first have to understand the two major roadblocks that have been holding swarm intelligence back. Okay, problem number one is something the paper calls the geometric capacity bottleneck. Just look at the slide. On the left, you've got this complex branching structure, kind of like a family tree. Now imagine trying to cram that whole thing into the flat square grid on the right. It just doesn't fit, right? It gets all squashed and twisted. Well, that's exactly what happens when we try to model complex systems on our flat, traditional computer grid. And this over-squashing isn't just messy, it's a total disaster for the swarm. It causes catastrophic information loss. Important connections get severed, agents get confused, and the whole system just breaks down. You just can't build a truly smart, scalable swarm on a foundation that's fundamentally the wrong shape. The second big problem is all about timing. It's called the temporal binding problem. Think about a flash mob for a second. How does every single person know to start dancing at the exact same moment? There's no big clock in the sky, no conductor. That's the challenge for our swarm. How do all the individual parts get on the same page and act as one? So we've got a space problem and a timing problem. How on earth do we solve them? Well, this is where the paper proposes a truly radical idea. What if the problem isn't the agents themselves, but the world they live in? What if we could just give them a completely new universe to operate in? And the answer, believe it or not, is something called hyperbolic geometry. Now, I know, it sounds like something straight out of science fiction, but it's a very real mathematical space. And it might just be the key to unlocking the true potential of swarm intelligence. So let's take a quick trip into this weird and wonderful new world. Remember that squashed tree from before? Well, in hyperbolic space, that's just not an issue. The space itself actually expands exponentially right along with the swarm. It's like having an infinite canvas to paint on. Suddenly, every agent has all the room it needs. No more collisions, no more lost information. The space problem solved. This is a great way to picture it. Hyperbolic space isn't flat like a piece of paper. It's negatively curved, like a saddle or a Pringle chip. And this unique shape is the perfect home for our swarm because it naturally allows for those complex branching hierarchies that we see everywhere in nature. Okay, so hyperbolic geometry gives our swarm the room it needs to grow. That's awesome. But what about the timing problem? How do thousands or even millions of these agents get in sync and learn to act together? The solution here is a really clever mechanism called H-AKORN. It's part of this bigger framework called Hyperbolic Neural Cellular Automata, or H-NCA. Basically, it's like giving each little agent its own internal metronome. They listen to the beats of their neighbors and then slightly adjust their own rhythm to match. It's such a simple, local rule, but the effect is incredible. A global rhythm emerges, and the entire swarm just finds a common beat completely on its own. And you can actually see it working. The results are just stunning. This chart shows how synchronized the swarm is over time. You can see on the left, at the beginning, it's total chaos. But watch what happens. As time goes on, the agents start to find their rhythm, and the whole system becomes more and more orderly. It's beautiful self-organization in action. What's maybe the most amazing part of all this? All of that complex, coordinated, intelligent behavior, it all emerges from this super simple three-step dance that each individual agent is doing. Sense, calculate, act. That's it. It's just a beautiful example of how mind-blowing complexity can come from the simplest rules. So what do you get when you put it all together? When you combine this ever-expanding hyperbolic space with these self-synchronizing agents? Well, you get something totally new. It's this idea of geometric intelligence, the notion that the right space plus the right rules can unlock a whole new level of collective intelligence. This H-NCA framework is a real game changer. It means we can start designing swarms that are more scalable, more resilient, and way more intelligent than anything we've had before. I mean, think about it. Swarms of nanobots repairing our bodies from the inside, or fleets of drones working together to put out forest fires. This is the kind of future this technology could make possible. And this is where it gets really wild. The authors even suggest that the unique shape of hyperbolic space itself could be a key to creating more lifelike, even creative AI. The constant curvature creates this kind of productive tension, they call it geometric frustration, that keeps the system from getting stuck in boring, simple patterns. It's like the space itself is nudging the swarm to constantly explore and become more complex. And that leaves us with a truly mind-bending question. What if intelligence isn't just about writing better algorithms, but about finding the right universe for those algorithms to live in? If just changing the geometry can create order from chaos, what other forms of intelligence are just waiting out there for us to discover, hidden in the very shape of space itself?